Hello students, welcome to yet another video lecture. My name is Tausif and the topic for today's lecture is traveling salesperson problem. First of all, we'll see what a traveling salesperson problem is. Now, if we have entities, if you are given with entities, a traveling salesperson wants to visit each of the entities exactly once, minimizing the distance traveled, total distance traveled. The goal here is to minimize the total distance traveled. And return to the starting point. So a traveling salesperson wants to visit each of the entities exactly once, minimizing the total distance traveled. So given a set of cities along with the distance between them, rather we may say the cost of distance between them, cost of the distance traveled between them or cost between them, we have to find the cheapest route from a city and returning to the same city. So our goal here is to find the cheapest route. Formally, we can define it like this. Given a complete undirected graph, are defined as GVE, where V is the set of vertices and E is the set of edges along with the non-negative cost for each edge UV that belongs to E. If we are given with a complete undirected graph GVE along with a non-negative cost, and if that cost is defined by C of UV for each edge UV that is in E, our goal is to find a Hamiltonian circuit of G with minimum cost. This is the formal definition of traveling salesperson problem. So basically what we are trying to do is we have entities. Let's say we have 5 cities here, and the salesperson starts with arbitrarily with a city, say this, and he has to visit each city exactly once and return to the starting city. There may be many permutations which he can take. He can go here, 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 and here. He can first go here, then here, then here, then here, and here. So there are many permutations and combinations he can use. But what we are interested in is finding a path, finding a circuit whose cost will be minimum. The cost of traveling that path should be, that circuit should be minimum. So that's our goal here. Now, in our goal, I have used the term Hamiltonian circuit. What a Hamiltonian circuit is, you should be familiarized with it, but if you are not, let me define it for you. A Hamiltonian circuit. It's a closed loop or a closed circuit of a graph that visits each node exactly once. This is known as the Hamiltonian circuit. The important thing to understand here is that each node is visited exactly once and it's a closed circuit. That means the starting and the end points are the same. So in general, one more time, the traveling salesperson problem asks us to find the cheapest closed circuit in n number of stages of a graph. Now, first of all, let me give you some examples of Hamiltonian circuits. Let me take a complete graph. If we have a complete graph like this, this is a complete graph, right? We have 5 nodes here, node number 1, 2, 3, 4, and 5. A Hamiltonian circuit would be if we start with this T here, go to this, and then go to this, and then go back to this, and here, and here. So this will be one of the Hamiltonian circuits. So this T is visited once, then this T is visited once, then this node rather is visited once, then this node is visited once, exactly once. This node is visited once, and at the end we are returning to the starting point. So starting and ending point both are the same, and this covers our Hamiltonian circuit. Let me take one more example. If we have a graph like this, if we have a graph with 4 nodes, a Hamiltonian circuit, if we start with this node here, a Hamiltonian circuit can be like this here, and then here, and here. So this will be the direction of our circuit. So we'll start with this T, go here, visit it once, go here, visit it once, then go back here, visit it once, and then return to our starting T. So this is our Hamiltonian circuit here. Now, if we have a weighted graph, when we are dealing with a traveling salesperson problem, we should have an undirected graph, but a weighted undirected graph. So we'll see an example of a weighted undirected graph, and then we'll see if there is a Hamiltonian circuit in that graph or not. If we have a graph like this, we have a graph with 4 nodes, and this is a weighted undirected graph. The weights are defined as 4, 3, 3. Let me say this is 1, 2, and 1. So this is the weighted undirected graph, and a Hamiltonian circuit would be, if we start with this node here, it would be, if we go from that node to this node, and then from this node to node this, and back to node number this, and then we'll go back to the starting node. So our Hamiltonian circuit goes like this, here, and then back here, and then to the starting point. And the cost of this circuit would be, the cost here is 1 plus 1 plus back here 2 plus back here 4. So the total cost of our circuit is 8. There may be one more Hamiltonian circuit in the graph. Again, I'll take the same graph, but I'll name it right now. Let me call it A, B, C, and D. The cost of AC is 1. This is 3, 3. This is 1, 2, and 1. The Hamiltonian graph we draw right now, if we draw a Hamiltonian graph from A to D, D to B, B to C, and C to A. The cost of this is A to D is 1 plus 1 plus 2 plus 4, which is equal to 8. If we take one more shot at this, if we take a graph like this, A to C, C to B, B to D, and D to A. Let me see. A to C, C to D, okay, C to D, D to B, and B to A. What will be the cost of this Hamiltonian circuit? It will be A to C is 4, plus C to D is 3, plus 3 D to B is 1, and from B to A is 3, right? And it is equal to 4 plus 3 is 7, 8, 8 plus 3 is 11. The total cost is 11. So there can be many Hamiltonian circuits of a graph, and our goal here is to find a Hamiltonian circuit with the minimum cost. And that right now is this circuit. A, D, B, C, and A. The problem with the traveling salesperson problem is that there is no deterministic polynomial time algorithm that can solve this kind of problem. No deterministic polynomial time algorithm exists that solves this problem efficiently. So again, we have to solve this problem, but we use approximation algorithms, which we have been using since the last 3-4 lectures to solve many problems which are NP hard or NP complete. So let's try and solve this traveling salesperson problem using approximation approach. Before we take the liberty to solve the traveling salesperson problem using an approximation approach, first let's define what a metric traveling salesperson problem is. Metric traveling salesperson problem. Now, this is very important. A metric space is a pair SD where S is a set. S a set may be a set of vertices or nodes or cities, and D is a distance function that satisfies for all UVW that are in S the following conditions. A metric space is defined by a pair SD, where S is a set of vertices and D is a distance function that satisfies for all UVW that are in S the following conditions. What are the conditions? Condition number 1. D of UV is equal to 0. Condition number 2. The distance of u, v, distance between u and v should be equal to distance between v and u, should be the same. And third condition is that distance between u and w plus distance from w and v should always be greater or equal to the direct distance u, v. These are the three conditions that our traveling salesperson problem should satisfy for it to be called as the metric traveling salesperson problem, and that's the kind of problem we will be trying to solve using the approximation algorithms. So this is the algorithm I'm going to write, the approximation algorithm for the metric TSP on graph G. If you are given with a graph, undirected weighted graph, our solution here, the approximation algorithm, should be able to find a solution which will be close to the optimal solution but may not be optimal. It will be a good approximation but will not be optimal, which we have already seen in our previous lectures why. Step number 1 here is we have to compute a weighted minimum spanning tree of G. The first thing we'll do is we'll compute a weighted minimum spanning tree of G. Second step is root G arbitrarily and traverse in pre-order fashion and our output will be V1, V2, dash up to Vn if we have n number of vertices in the graph. And the third step will be output tour will be given as V1, V2, dash up to Vn and back to V1. This will be our tour, the tour for the traveling salesperson. So we start with computation of a weighted minimum spanning tree. This is a new term and we'll define this in a while, minimum spanning tree of graph. Then we'll root G arbitrarily. We can take any node and designate that node as our root, and then we traverse the graph in the tree rather in pre-order fashion, and we'll get the result as a sequence of nodes, and then we'll output the tour as V1, V2 up to Vn, and then we'll go back to our starting node, and that will be our tour for the traveling sales person. This is the solution given by this approximation algorithm. Although this algorithm is not, it doesn't give always the optimal solution, but the solution provided by this algorithm is a two approximate solution. Which means that the solution given by this algorithm will never exceed the amount or the cost twice the optimal solution. For example, if the optimal solution is A, this solution will always be less or equal to 2 times A. It will never be greater than 2 times A. That's why this solution is known as two approximate solution. Let's see some examples now. Okay. In our first step of the algorithm, we had defined that we have to compute the minimum spanning tree of the graph G. A minimum spanning tree First, let's define a spanning tree. A spanning tree is a subgraph of a graph that connects all the nodes together. It's a subgraph of a graph that connects all the nodes together. Then what is minimum spanning tree? It's a spanning tree with the lowest weights than all the other spanning trees. A graph can have multiple number of spanning trees. A graph can consist of subgraphs, many subgraphs that connect all the nodes together. But we have to find a spanning tree with the lowest weights on the edges, the lowest possible weights on the edges, and that's known as the minimum spanning tree. For example, if I have a graph like this, A, B, C, and D, with weights given as weights given as this. There can be many spanning trees for this graph. Let's draw all of them one by one. One of the possibilities is this is one of the possibilities. This is one more possibility. Let me draw all the possibilities. This is one more. It's A, B, C, and D. This is A, B, C, and D. This is our A, B, C, and D. So one more possibility. More spanning tree. This is A, B, C, and D. If we write the weights on edges of these spanning trees like this, it will be 3, 4, and 8. It will be 3, 6, and 8. And this will be 4, 6, and 1. These are all the spanning trees possible from this graph G. These are all the subgraphs that connect all the edges, and these all are the spanning trees. Now, the minimum spanning tree is the one with the minimum weight. If you count the weight for this tree is 819 plus 3 is 12. 8, 3 is 11 plus 4 is 15, 6, 1 is 7 plus 4 is 11, 6, 8 is 14 plus 3 is 17. So this is the minimum spanning tree for this graph. Coming back to our approximation solution for traveling salesperson, metric traveling salesperson problem. Well, let's say if we have a graph like this, it may be 4 stages. With weights given as name it as A, B, C, and D. The approximation metric traveling salesperson asks us to compute a minimum spanning tree for this graph, and that will be given as this. This will be the minimum spanning tree for this graph. And then the second step is to take any node as root, arbitrarily take any node as root, and then traverse in the pre-order fashion. Now, if we take A as the root, D, and we traverse, so our output will be, if we take A as root, A, C, B, and D. And our final tour will be this, the third step of the algorithm. A, C, B, D, A. This is the tour we'll be taking, the traveling salesperson should be taking to minimize the total cost of his travel or distance. Even though this route may not be optimal, it may be a bit over than the optimal cost, but this algorithm is the only algorithm possible that can be solved or executed on a machine, deterministic machine, in polynomial time. And the cost of this approximation is that it can be a 2 approximation problem. But the happy part about this is that we were able to solve this problem, which was in fact, in reality, an NP hard problem. Thank you.